Okay, starting from electrolysis of dilute sulfuric acid solution, we're still using the inert electrodes. This can be platinum or this can be graphite electrodes. Well, platinum and electrodes are definitely a better choice, but the only problem with them is that they are expensive. Look at the structure, you'd understand that this time the electrolysis structure is a bit different. Yeah, the scientists made it a little bit different in order to keep the process running and keep getting the gases out of it. So we have the power supply at the bottom, because of which we have the positive and the negative compartments. We have platinum electrodes mentioned properly. We have this huge portion that is filled up with water. The inlet comes from here. It is dilute sulfuric acid solution. So a little amount of sulfuric acid and a lot of water is added. Now, if you take a look at this, you would understand we have two products and both of them are gaseous products. This should make sense. The sulfuric acid is this. Dilute sulfuric acid, it means an aqueous solution. This is going to give you H positive ions. This is going to give you the sulfate ions, the negative ions. Aqueous means it's going to give you H positive out of water and OH negative out of water. Okay. Since all the positive ions are hydrogen ions, so we can't get anything in terms of positive part or cathode compartment. So we only get at cathode the hydrogen gas. And the equation is pretty simple. If you have practiced the table that I gave you, and as you say, you
Mhm.
must be very familiar with this equation, and this shouldn't be a problem for
Yeah,
you. You might have already memorized the equation, you might have
yeah,
written it so many times. Okay,
yeah. Mhm.
right, good. And on the other side, of course, this is the anode compartment, and we have oxygen over here. Now, this makes sense that we have a polyatomic ion, SO4 negative 2, versus this OH negative. And we do understand in case of all polyatomic ions, only the OH negative goes to the electrode and forms oxygen by and as I tend to say, rati-rati equation. Yes, so you are going to come up with this equation. All right. Sulfate ions
Yeah.
are actually difficult to oxidize, as mentioned over here, or you may also say sulfate ions are reactive. They tend to remain in the solution. So what happens is that some of the hydrogen ions and some of the sulfate ions tend to remain in the solution, and they keep the sulfuric acid ions in there. So what got back to this is that OH was converted into oxygen over here, H was converted into hydrogen over here. But if I look at this, I find that this and these heights are exactly twice of one another. If this is one, this is two in terms of height, double the height. And this
Mhm.
pretty much tells us that since the formula of water consists of two hydrogen and one oxygen, so this hydrogen and oxygen ratio stays the same over here, 2:1. Twice as much hydrogen is produced as oxygen. Look at the half equations for every four electrons. And this is the explanation of it. For every four electrons given out when oxygen is formed, we can use two of them to produce one mole of hydrogen, and again, two of them to produce second mole of hydrogen. So four electrons would produce two molecules of hydrogen or moles of hydrogen, whatever you'd like to say. Both ways it's fine. So twice the molecules of hydrogen as of oxygen, or twice the volume. It uh, covers twice the space. So this experiment can tell us about the structure of water, all right? So
Mhm.
when we do this experiment, we get more amount of hydrogen, we get less amount of oxygen. This is also because oxygen is soluble in water. Now, this specific piece of information, this line, oxygen is more soluble in water than hydrogen. Hydrogen is actually an insoluble gas, oxygen is slightly soluble gas. So this piece of information is actually something that we are going to cater in detail in chapter 18. But before that, this single line can work good enough for you. So what would happen is that we'd get less oxygen because some of the oxygen will be dissolved in this water. We'll get maximum amount of hydrogen because hydrogen does not dissolve in water. This won't go down,
Mhm.
right?
Yeah.
So we what we do sometimes to stop this from happening is that we carry out the electrolysis experiment for the first few minutes in order to saturate the water or fill the water with oxygen. Then we start collecting the gases. This gives much better results, and this definitely gives the 1:2 experimentation in a better way. Well, this is just a piece of information when you are actually going to carry out the experimentation. Not that it is going to be a part of exams. I don't think they are going to use this as a question. Well, this can definitely be used as a question, and I've already explained how the formula can be confirmed from this experiment.
Mhm. Yeah.
Right? You want me to go through this part too? Electrolysis of other solutions?
No.
Okay, this is a summary. We're done with this summary as well as the examples. I hope this is clear. What about this part, non-electrolyte? They're not going to conduct electricity, so of course nothing's going to happen to them.
Yeah. All right.
Okay, so let's move on to quantitative electrolysis. Now, previously, what we were doing was completely qualitative electrolysis. When I say the word qualitative electrolysis, what I mean from it is that we are trying to talk about what substances was a compound made up of, or what it gave in terms of product at cathode or anode, or as the result to the or change to the electrolyte or the solution. That is all qualitative analysis, electrolysis is all about. Remember, qualitative and quantitative are two words that we put with electrolysis or with any kind of analysis. What is the component made up of is qualitative, and how much of that component are required is quantitative. For example, if I do a test on water and confirm that water is made up of hydrogen and water is made up of oxygen, this analysis or this electrolysis would be qualitative. I told you what the components are. And if
Uh-huh.
I tell you that the ratio of hydrogen and oxygen is actually equal to two atoms and one atom, then if I start talking about the quantity of these atoms or ions, then I can call it quantitative. That's what is the difference between quantitative and qualitative. Qualitative only talk about the components it's made up of, and quantitative discusses the exact amount, the numbers we need to prove how much is in there. For example, if I do an analysis of tea, a very common beverage in Muslims, right? So the qualitative analysis would tell me it's made up of milk and sugar and tea powder. And the quantitative analysis would tell me how much of milk was used, whether it was half a cup or a full cup, or how much of tablespoons of sugar were there, or how much of tablespoons of tea powder were there. Quantity, quantitative, quality, what it is made up of. All right. This is going to
Yeah.
really help you all along. I have defined this at this chapter. Well, it's not going to really help you much with this chapter, but it is definitely going to help you a lot with chapter 18. Knowing it now will help you excel through chapter 18 without having to go through this discussion. Okay, so moving on, as he starts with the same thing related to numbers, how much is what we are going to investigate. For example, investigate the effect of changing the current on the amount of hydrogen. If we increase the current, do we produce more hydrogen? That could be a very simple question that we can answer with the help of quantitative electrolysis. So, in order to do this, we set up a similar apparatus. We have the figure 10.6, and this 10.11 has similar kind of apparatus. But what we changed over here are a couple of things. we have to put a variable resistor over here. As the name
Yeah.
suggests, this is going to add resistance, and the resistance can be varied as per our requirement. We have also added an ammeter in there to allow the vary and measure the current we are putting. So as soon as we increase or decrease the resistance, we know how much current is flowing through the system. So the resistance would be controlled with the help of variable resistor, and the amount of current flowing would be identified with the help of ammeter. The rest of the apparatus is fine. We have a battery or a power pack. We have the two electrodes connected to each end of the battery. We have the rubber bung. We have the glass tubes. We have the inverted test tubes. And this time we have the test tubes that are graduated. Look, you have readings on there 5, 10, 15, 20, goes all the way to 50. All right. Since we're
Yeah.
doing quantitative electrolysis, so the quantity does matter. All right. So
Yeah.
you would see these in case of quantitative. In case of qualitative, you need simple. You don't need the graduations or the markings on them. So set up the apparatus as shown, and then you go ahead with pouring 50 cubic centimeter of concentrated sodium chloride solution in the glass tube. You place a gas burette measuring cylinder filled with sodium chloride solution over the cathode. As soon as you do, you turn on the power pack, connect it to battery, set the current to zero point 0.2 amperes. We're starting off with a smaller value and we're going to increase it step by step. Moving on, we take the initial reading on the burette. We have to start the current flowing so we can see what the current is. Therefore, we can only take the reading on the gas burette after we have turned on the power. So the first reading would be after turning on the power. Start the timer. Stop the timer after 5 minutes. Note the final reading on the gas burette and repeat it for zero point 0.4 amperes, zero point 0.6 amperes, zero point 0.8 amperes, and finally 1 ampere current. Now, you'd notice that the volume of hydrogen gas production from the burette readings is also given over there. Repeat each experiment to get more reliable results. You can repeat them twice, you can repeat them thrice, it is entirely is up to you. Then what you can do is take these values of current, put them in x-axis, take these values for volume of hydrogen in cubic centimeters, put them on y-axis, and draw a graph about it. Now this graph can exactly tell you, after drawing a straight line, which experiments were done correctly in this whole situation and which experiment was a failure or you made a mistake in that. What the mistake was will be pointed out, and of course, if I extrapolate it, you'd get to know what the exact value should have been if the experiment was done correctly. All right?
Yeah.
Means if I extrapolate it currently, I have this much volume of this coming out, but it shouldn't be this. I'm sorry, my bad, my lines are wrong. This is the right line, this is not the right line. And what it should have been is something like this. So this reading is incorrect. It should be closer to 21 or something, 21.0 or something, as what I extrapolate from this graph. Okay, apart from these calculations that I just made, now a few things to note. Let's go with the lines in the book. Because the current is continuous data, we draw a line of best fit through the points. The reading at zero point 0.6 ampere is an anomalous point. Of course, that's an odd point. Anomalous means odd, probably not correct, probably not fitting through the line. We do not include this when drawing our line of best fit. The reading of zero point 0.6 amperes is too low and could have occurred because of the current that we used was too low or some gas escaped. It can be any of those problems. Line of best fit is a straight line that goes through the origin. And so we can say that we have a proportional relationship, which means as soon as we keep increasing the current, the volume of hydrogen per cubic centimeter also increases. These two are directly proportional to one another. Increase the current, you'll get more volume of hydrogen produced. Make sense?
Yeah.
And that's about it. This was the only point we wanted to prove out of this quantitative electrolysis. It means more the strength of our current, higher or bigger yield you are going to produce out of it, which means if electrolysis is actually expensive, and as we have studied that in the reactivity series chapter, you do get an idea of why electrolysis is so expensive. I kept saying it was expensive because it was using current. Now notice it's not just it. It's not just about using current and that's why it's expensive. It's also because of the fact that more current we use, the more hydrogen or the product we can produce. So we try to be a little bit greedy. We can produce more if we use more current. That's where the electrolysis becomes expensive and expensive because we try to use higher and higher strength of current in order to produce more. I hope you get the point, right?
Yeah.
Good. Mm. This finishes the chapter. Any questions?